Okay, all set. Good. So, so again, full disclosure, I have seen the question that the test student will get. It was simply necessary so that I don't, when we start at random, it's not one of the questions I've already done. So, let me get started. And I think I've mentioned this before. 20 minutes is not a lot of time. So, once I start, I'll try to be quick about it, not waste too much time. Well, I don't know if it's a waste, but I'll watch the time as I explain any of the things I'm doing. So I'll try to be mindful of this 20-minute time limit. And again, when you are doing the timed assessment, what I recommend is within the time limit, focus on getting the correct answers or, answers, the progress toward the correct answer that you can put into the answer box. The scratch work, you can have time to organize it after the time limit runs out. So during the time limit, you should be focusing on answers that you are putting into the answer box. So with that, let me start the question and we'll go from there. And yeah, no outside help. It is open book, but all right. So this is the question. In this question, we will explore oddities and realities of interstellar. So long. I'm just gonna read it silently. There is a kind of device for the question. We're going to assume that observers can make observations instantaneously, which we know physically is not possible, but that'll simplify our description for the purpose of this question. In sci-fi, there's a device called Ansible that you see sometimes you see. Enter text if figures needed. Okay, Enterprise 860 mission to Rigel, which is that far away from Earth. So Enterprise must be traveling pretty much at speed of light. Yeah, to 99% of speed of light. And it makes most of the journey at this speed. And what do they see? Show your brief calculations and explanations below. Okay, so there's one number that I do need. So we know the speed, let me call it beta of 0.99, and the proper length or distance, let me just call it the distance that they'll be traveling is 860 light year, which means if we need the travel time from Earth frame, it's going to be basically this 860 years, or it's c times years for light year, divided by the speed, 0.99 c. So we know it'll be very close to 860 year within 1%. That's kind of how it's set. The other number that I need, that's a kind of calculated number, is I need a gamma that corresponds to this beta. So gamma is given by 1 over square root of 1 minus beta squared. And I need a number to work out the time dilation factor and all this stuff. So let me do that in Wolfram alpha. I'm not using this as search engine, it's just a calculator. 1 over square root of 1 minus beta squared. Then I prefer this over a scientific calculator. Oops, not 0.99 squared. Because I can make the changes more easily. So 7.09 is going to be the gamma factor that I'll use. 7.09. So, how long does your journey take as observed by mission control? So the journey from the mission control's perspective, it takes the regular amount of time one would expect. Duration is equal to distance divided by speed, or 860 c times year for light year divided by 0.99 c is equal to, let me just get a more accurate number. So it'll be 860 with 0.99 or 860 8.7 years. 868.7 years. What would the mission control observe within Spaceship Enterprise, is including science of passage of time? So time dilation effect occurs. moving clocks in the enterprise are slow, so the amount of total time that passes for enterprise passes according to the enterprise clocks is so the proper time in the mission control frame is 68.7 years divided by the gamma factor. Um, I'll give the number and then in parentheses give the gamma factor. So this number divided by the gamma factor, or oh, I guess I can keep it accurate. So in that case, I divide by 1 over square root of 1 minus 0.99 squared. So 122.5. Wow, people will have died. 122.5 years. Guess that's not fast enough. Gamma is about 7.09 with a beta equals 0.99. Okay, 3. What happens as the spaceship Enterprise comes to a stop at Rigel? Not much. Nothing remarkable, really, at least for the observers at the mission control. Because it's I mean there could be some effects that's comparable to general relativity, like the acceleration that's equivalent to gravity, but I think you can set it up in a way where all those are negligible, so nothing remarkable really. So that's A. In B is where understanding of special relativity is tested. So what the crew of a spaceship Enterprise will see, observe, and experience through brief calculations. How long does the journey take? So we've actually worked this out. How long does the journey take? The journey takes about 122.5 years, which is the amount of time the mission control sees or observes as passing according to the Enterprise clocks. And let's see. We can also get this number through length contraction. From the Enterprise's perspective, the distance of A60 light years from Earth to Rigel is length contracted by a factor of gamma equal to 7.09. So they are really only traveling the distance of, let me get the number, A60 divided by, I'll just do the same things, 1 minus 0.99 squared. So 121.3 light years. 121.3 light years. And at relative speed of 0.99 c, this distance is covered in 122.5 years. You can do the division to make sure that works. What would the crew observe if they use their Ansible to observe mission control during their journey? So, um, I will limit the scope of the question. So, in the middle of their journey, Earth clock for the observers on the spaceship Enterprise is the moving clock and is therefore time dilated in the amount of time it takes for the Enterprise clock to count, I don't know, about 7 hours. The Earth clock will pass only on hour. In other words, so more pointedly, Uh, for the most of the 122.5 year journey, Earth clock passes only let me do that number. So that number of like 122.5, that was the right number of years, right? Year journey. That divided by the gamma factor, 1 over square root of 1 minus 0.99 squared. 17.3 years. It passes only 17.3 years. So, yeah. And I say most to cover the last part. What happens as the spaceship Enterprise comes to a stop at Rigel? So, the biggest change that occurs um, as a Enterprise comes to a stop is the sense of simultaneity shift. I'll say C, attach the figure, and attach a space-time diagram. And the space-time diagram that, let me see if I can do this correctly in a relatively short amount of time. 9 minutes. How much could, yeah, C is not, I don't think that, maybe C is hard. So I'll draw a space-time diagram later. Space-time diagram. Um, so with access to a device like Ansible, the Enterprise crew will observe that Earth clocks from having passed only 17.3 years for the most of their journey as they come to stop at Rigel. They will see the Earth clock advance the remaining number of years. And this is gonna be basically the total travel time, 868.7 years. 868.7 years minus the 17.3 years. So that's, can I do this in my head? Not quickly and not, make it more quick to do this. 851.4 years. 851.4 years over however short duration of time. Let me use the chime thing. Over however short duration of time they need to come to a stop. That's 3. Oh, wait, that's 2. Wait, 2? No, that is 3. Okay, I think we're good. Yeah, what I part of 1 and 2 is it? I'm not sure what that question means. Let me do C, and then in any remaining time, I'll draw a space-time diagram and fix up anything that I missed in my response up there. So C, I thought I saw some sort of dynamics question. Yeah, in order to the awareness, there are the barriers. Accelerating. Yeah, how do you accelerate? Yeah. So this is dynamics. Look at what might be possible within the constraints of conservation of energy and momentum. So suppose that it has a reactor fuel. So let me draw this diagram for C. So I got a thing, and the fuel is actually going to be most of this thing. So this is the reactor fuel, starts with some SM. For the best case scenario, assume that somehow to possible turn this reactor fuel into massless particles, so that this whole thing, as the thing accelerates, basically what used to be that mass M will be ejected backward at speed C, and this payload portion will be the remaining part that's moving forward at speed v of 0.99 c. So they can be, yeah, or yeah, approximating this as a process that occurs at an instant, which will kill everyone on board, but just, back of the envelope calculation. Yeah, calculate what fraction of mass m is the payload mass m. Yeah. So payload mass m, how small is it? And I guess the capital M is actually the whole thing. It's not just the fuel. It's a fuel plus the uh, yeah, it's a space and the spaceship plus the reactor fuel. That's the total mass big M. So so as the question suggested, we use conservation of the relativistic energy and relativistic momentum. So let me write it down and then we'll go from there. So our starting energy is the the rest energy. So it'll be just capital M C squared. That's our um, initial state here, just with the rest energy of this. And our final state here will be I have relativistic energy of the propellant. Let me call this energy of the propellant, whatever it is. Plus, I have relativistic energy of the payload. That should be gamma mv, wait, not mv, gamma mc squared. So that's energy. For the momentum, we are starting with a zero momentum. And for the momentum of this propellant part, I can lean on this energy momentum relationship that E squared is equal to mc squared plus pc squared. So for massless particles like these, this is zero. So I can say momentum is equal to E over c. So for the momentum of the propellants here, I can say it's minus the energy of the propellants, EP divided by C, plus now I need the momentum of the payload, that'll be gamma mv. And if you count between gamma and v as just one unknown, because I can relate the two. In fact, the very next step, I'll rewrite v in terms of gamma. So if that's counted as one unknown, then I have one unknown gamma and another unknown ep. No, wait, gamma is known. It's a 7 point whatever. So gamma is known and v is also known from that. But what is unknown is a small m here. So, in any case, even though both the gamma and V are known, for calculational simplicity, I think I'm gonna still do the simplification that I'm gonna do. Not all the time. So, the thing that I need to do is, gamma is equal to 1 over square root of 1 minus V squared over C squared. Inverting this, I get V is equal to C. I have this memorized. Square root of 1 minus 1 over gamma squared. Do this often. So let me rewrite this side here. Minus EP over C hasn't changed. Plus, let me write this part first. It's going to be M times this, C times the square root of 1 minus 1 over gamma squared times this gamma here. And this is the simplification. When I absorb gamma in, basically I get gamma squared for the first term. And this gamma squared cancels that. So for the second term, it becomes just a 1. And gamma has been absorbed into the square root. So I got two equations. This is just going to be a numerical thing that I can plug numbers into. So let me just eliminate EP and do that. Oh, so I can imagine multiplying both sides through by C. Then this C becomes C squared. This goes away. Then I can do linear combination of equations 1 and 2. So if I write down 1 plus 2, that looks like left hand side is mc squared, right hand side EP cancels out, and I get, let's see, I got common factors of mc squared, and these gamma plus square root of gamma squared minus 1. I think, yeah, so easy last step to solve for m. M should be equal to, C squares having cancelled out. It's going to be a fraction of the mass M, which is what I wanted. And that fraction out to be 1 over gamma plus square root of gamma squared minus 1. And I think I can work that out later above. So x in m is equal to x times m is equal to, is given by x is equal to 1 over gamma plus square root of gamma squared minus 1, where gamma is equal to, from the numbers above, I think, 7.09. Oops, 7.09. So x is approximately equal to, let's do this, 1 over 7.09 plus a square root of 7.09 squared minus 1. It's very small a fraction, 7.0, well, 0.0709 or 7.09%. 7.09%. So yeah, even this, with this fantastical assumption, um, again, huge majority of that initial starting thing has to be the things that's going to disappear, which means, how are they going to stop at the end? It's like stopping will basically take this down to 7.09% of this, and then coming back will be another 7. It's like, it's you need basically a new technology. It's, yeah, like, it's impossible. It's not something that's practically can be done. And usually in sci-fi, they invent some new thing like a warp engine or like a space extending bending thing. In the three-body problem, the author imagines like a propulsion mechanism that manipulates the space in front and behind of the spaceship. So, anyways. So one thing that I did want to finish, and I did this. I knew I was gonna run out of time, so I want to draw a space-time diagram that I'm describing as, C attached, and doing this is perfectly fine as long as you are doing this. So I said C attached space-time diagram. If you are drawing it after your time limit has run out, that's fine. Although a lot of times you kind of need that diagram to reason things through. But if you feel like you know the stuff well enough to do that, like do what I'm doing, have had it worked out in your head, and you are now uh, finishing up the diagram after having actually answered the question. That's also fine. And the truth is, for your student answers, it's not really expected to be as detailed and thorough for completeness. So I think what I can imagine is, I can imagine a world line of a spaceship Enterprise with a bit of exaggeration, as in 0.99 will look really close to this line, but I'm gonna draw it a little bit ahead, a little bit separated, so that they can be distinguished from that light world line. So this is gonna be a world line of Enterprise, and that also happens to be the CT prime axis while the Enterprise is traveling. And this is the sense of simultaneity while the traveling is occurring. So this is the x prime axis in that reference frame. It's really hard to draw because it's trying to draw something with a slope very close to 1, but not 1. And symmetric to that. These two angles should be about the same. So x prime. So that's the sense of simultaneity. So if you imagine this is where Rigel is, and if you imagine this is the kind of the event where the Enterprise is coming by the Rigel, then what they observe back on Earth is basically along this line of simultaneity, one where these two are parallel to each other. So this, when they observe Earth back with the Ansible, this is the Ansible observation while moving, while at beta equals 0.99. And that's along the line of simultaneity that's in effect while they are traveling. As they come to the stop here, their space-time axis becomes basically the same as Earth, just with the origin shifted over. So once they come to stop here, then their x double prime axis is this, because then you will be at rest relative to Earth, and this will be their CT double prime axis. So according to this new sense of simultaneity, the kind of the points on Earth, the observation point on Earth at the same time while they are here at the same moment in space time, same space time event, but in a different reference frame. This should be unstable observation after stopping. And it's the question of, okay, how long does it take for this observation to shift over to this? This is basically, this happens over duration of stopping. So if you imagine they can stop instantaneously, which again will kill everyone on board. But if they can do that, then yeah, instantaneously, one moment they would have been seeing this, and the next moment after stopping, they would see this. If it takes them a year to stop, then okay. Then 1 year ago they saw this, and a year later, Earth clock has jumped forward by 851.4 years. So, and plus 1 year. So yeah. So that's what I will attach as I attach work. So all right, let's do that. Let me attach, and I'll attach them slightly out of sequence so that it's in the order of A, B, C. I don't need to confuse my grader with the out of sequence work. Right after I submit, attach the work, and we'll just double check the answer key to make sure I didn't make any mistakes. I know I wouldn't have made any conceptual mistakes, but I could have made calculational mistakes. So we'll double check to be sure. so that's my work. This is the questions you can see in Freeform timed assessment for special relativity. Some of them are more heavier on relativistic kinematics, which is like this question. Some of them are heavier on relativistic dynamics. This had a small bit of dynamics part, but most of it was relativistic kinematics. And there will be other questions where they are heavier on relativistic dynamics. Here's the test student's attempt, the same question. Here are the answers. So let's just check with answer key. Journey takes, 68.7 years. Yeah. I'm very consistent person. I say things in a very consistent way. So 2 times dilation, it's gamma factor. So 123 years will be observed to pass. Nothing remarkable happens. Again, remarkable. Nothing remarkable. Yeah. Oh, yeah. This is what is it? Heinlein is, I think, the author who uses this particular idea. Not the Ansible, but the Howard families. Robert Heinlein. Anyways, B. These answers, answer key. And yeah, I might actually replace this drawing with this after I clean it up. We'll see. A lot of this comes from my previously written, like handwritten answers, and I think that this diagram might be cleaner. Ooh, I'll see. I might replace it. 23 years. Yeah, won't feel like there's time dilation. Yeah, they will just feel normal, and in fact, you can get it through length contraction. Yeah. So. Mission control, 17.3 years pass, 17.3 years pass, As they come to a stop, their sense of simultaneity shifts. Is that the exact phrasing I use? I think that's just me. I don't know if other people use the same phrase. But it does have to do with the relativity of simultaneity. It depends on depending on what reference frame you are in, what you observe as simultaneous is different. So, all of that. Yeah, I'll probably replace this figure with I'll to clean up the writing, and I'll replace the figure with this. I'll do that off recording. I can do it later. Um, yeah, after stopping, they'll say that this many years have passed. Yeah, showing the perspective. Yeah, good. Here, let's hope I calculated 7.09% correctly. Let's see. The solution might use different approaches. Maybe, maybe not. Yeah, slightly different. I think a solution simplified the things a little more. Um, doesn't matter. Or not. They just left it in terms of V. But 7.09%, yeah, that's it's very so interstellar travel it's unless somebody literally invents a warp engine, it might remain science fiction for the rest of human history. Who knows? But Mars, we can probably get to, possibly even within my lifetime, depending on improvements in technology. It is still very impractical because, but like getting to Mars, we've sent things to Mars. It's just that establishing a colony there is different from sending rovers there, remote controls robots to explore. So anyway, so that's this question. A bit depressing depending on how you look at it, or it's a special relativity question, so it's not designed to be depressing. But special relativity puts depressing constraints on what's uh, what's possible in terms of interstellar travel. So